Okay, so in this lecture we are going to start unit number 3, a concept. Okay, if you look clearly on this blackboard or whiteboard, basically I have drawn the two-dimensional representation of silicon semiconductor material. And in silicon or in any semiconductor which is of group 4 element, 4 valence electrons are in the outermost orbit. So now if you look clearly in this picture now, the 4 outermost electrons are marked as red, and these outer foremost electrons are making a covalent bond with another neighboring silicon atom as shown in the picture. Okay, but in reality, when anyone asks you to draw the p type or n type or silicon structure, the representation was different. Why those representation we are using, I'm going to tell you the reason of that. And first of all, this is the two-dimensional representation of silicon. Remember that this is not a three-dimensional representation. Silicon in three-dimensional looks very scary, not good at all. But in two-dimensional structure, to define any physics or to discuss or elaborate on any physics of semiconductor, this two-dimensional representation is more than enough. Now I'm going to take these two-dimensional representation of silicon to demonstrate so many things. For example, I have seen so many videos and so many notes and books also. A lot of time we are getting confused by so many things in the written in the book. Why we are getting confused? Because we don't know exactly the physics of semiconductor. We are just mugging things up. Okay, so now this picture is clear in our mind, sir. In the class only you have told that now this whole silicon representation, this is the front view, and at the back side of the or inside the board, these silicon atoms were represented like this. For example, whatever we are seeing is this one. At the back time, same structure is repeating itself, replacing itself. If you replace this is basically the exact scenario. All the silicon atom which we are basically seeing, and likewise this is the structure. So at the bottom of this silicon atom there will be some silicon atom, and likewise this is basically a structure. Now in the class only you told us this whole sample is basically kept in a chamber for the doping purpose. Doping means addition of impurities, whether we want to add trivalent impurities or whether we want to add pentavalent impurities. Now the whole structure or whole this silicon, pure silicon atom was inserted in a chamber, and now inside the chamber this is basically the front part. For example, if this is basically your silicon sample, now this is a silicon sample. Now this is the front face of your silicon sample. Now this is the structure. Now these all these silicon atoms, and below that all the silicon atoms are basically the front space of your silicon sample, and they are kept in a chamber. Inside the chambers, vacuum is created. Vacuum is created, and simultaneously the pentavalent impurities, if we want to dope a pentavalent impurities, for example the phosphorus atom was inserted. If we want to include the pentavalent impurities, if we want to include the trivalent impurity, we can insert, instead of phosphorus we can insert boron. Now let me take first example. In the chamber we have inserted this sample. Simultaneously phosphorus atom was inserted, and inside the chamber the temperature was slowly raised up. As soon as the temperature is getting raised up at near about 100 or 1000 degrees centigrade, or we can say that 1100 degrees centigrade, what happens, these silicon atoms are basically getting ejected from their places. Now, initially, as the temperature increases, this silicon atom moving like this one, a time will come at a specific temperature or 1100 degrees centigrade, this silicon atom will come out of their places. So this is basically the front face of the sample. So first of all, this silicon atoms, all these silicon atoms are getting ejected from the surface and from the surface, simultaneously leaving a space behind. At this space, these pentavalent impurities, if only pentavalent impurities are present, these pentavalent impurities having 5 electron, 1, 2, 3, 4, and 5. The silicon atom is having 4 electron, pentavalent impurity is having 5 electron. These phosphorus atom which are present inside that chamber, they are getting placed on the space available due to the vacancy created by the silicon atom. But the phosphorus atom have 4 electron. These 4 electron will take part in the covalent bond formation, but there was one extra electron which is free to move. Out of these 5 electron, 4 electrons are basically involved in covalent bond, but 1 electron will be free. Likewise, at each and every place, these phosphorus atoms are basically placed, this phosphorus atom, and each phosphorus atom have one extra electron like this. Now if the temperature was maintained for a long time, after the front is facing surface, inside surface silicon atom will go on or getting ejected from the surface. Likewise, now this silicon atom will be ejected, and simultaneously or in the same manner, all these electron will be getting replaced from their surface, and this process is called adding or adding impurities, and another term, this is called doping. So doping is nothing a process in which the silicon atoms is replaced by another atom, and the addition of this another atom is basically called doping. And what exactly the doping will do, I will tell you after writing all these things. So here also phosphorus will come, and here also phosphorus, and here also phosphorus, 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 and phosphorus, and likewise these phosphorus atom will come, and with an extra electron, this extra electron, this extra. So if you look carefully in this, we have stopped the temperature, or we have reduced the temperature. So now this silicon atom will not get is replaced or get ejected from the surface, only this much will be replaced, correct? Now if you look into this region carefully, if you look this region carefully, in this region now there are so many covalent bond, yes, but having extra electron, each electron. Now this extra electron is basically, because of this extra electron, this region was named as a n-type region. So these are called n-type region. Why it is n-type? Because it is having extra electron. An electron is basically negative, and that is why this n name was given. So this is n-type region. Why it is n-type? Because you have inserted another atom, and these atoms are creating one extra electron, and these extra electron have charge n, and that is negative. So that is why this region is called the n-type. So now this is called n-type material. In n-type material, this is basically produced by doping pentavalent impurities. Now if you look at this n-type region, extra electrons are there. So now if you look downward, sir, up to this region, if we click out, okay, so if why we want to draw in this region, we want to see what is extra. There are so many covalent bond, but what is extra? Sir, extra electrons are there. So that is why this n-type region is represented like this. This covalent bond is not shown to for the simplicity only, but in the back of the mind, we being a student must remember that in n type not only the electrons are present, free electrons are present, but there are so many covalent bonds still present. And while explaining or while learning some concept, we skip these things, that this reason have electron, and this is the representation you will often see in books. In books they will show this is n-type region, and n-type region lots of electrons are there. But in the back of the mind, we being a student must remember these are the extra electrons, holes, extra electrons. Covalent bond is still present in this region also. In n-type, covalent bonds are present but not shown for this simplicity. But while understanding the concept, we require this covalent bond to explain any physics. And that is why we often do mistake, because most of the time in book or anywhere, if you see, they will draw this picture directly. And when they draw this picture directly, and we see that there are, in n-type region there are so many electrons. Yes, there are so many electron, not so many electron, extra electron. And that is why they are represented. Okay, now similarly, if we place this sample again in the chamber, but in this scenario keeping this face as a outward face, for example, this is kept out inside like this one. So this is chamber, and this is the face facing this to the chamber. Now again we have started increasing temperature. Now what will happen? Instead of the downward phosphorus atom, this silicon atom will be getting ejected from their places. So now likewise these silicon atom will get ejected because of the temperature from their place, leaving a space, and this space will be acquired by another atom, which I will or we will place inside the chamber. So this is the, now we have stopped this. And now similarly in this scenario we have inserted one boron atom in the chamber. Now this boron atom will take acquire these spaces which is created by the ejection of silicon. But in boron, what we know, boron have only 3 outermost electron. So now as soon as the boron will sit here, so boron have 3 electrons, so 3 electron will be this electron will form a bond, but this will create a hole or space. So this is not an electron, this is basically a hole, that is vacancy of electron is nothing but the hole. So likewise, everywhere instead of electron, one hole was present, boron hole. Likewise boron, and likewise, but having not extra electron but have hole. This is hole, and this is hole. Similarly, this is hole, and this is basically similarly hole. And now this is also hole, and this is also hole, and this is also hole. Now hole, this is boron, this is boron, and this is boron, this is boron. If you look this picture clearly, there are so many covalent bond is still present, but extra are holes, extra are holes, extra are holes. So if you look this region, whole region, this region will be drawn like this region have extra holes, and this region is called p type. This region is called p type. P for positive. Why it is p region? Because in this region lots of extra holes are present because of boron doping or boron including or boron insertion. So this is basically a p type, this is an n type. And now this is the exact representation which you see in books. This p type, basically if you see p type, they will draw p type having large number of holes, and this is an electron, or n type, so large number of electron. And this picture we often see, but from now onward we will remember that not only this representation we will remember, but in the back of the mind we will remember that this p region have lots of covalent bond, and this n region also have lots of a covalent bond. So inside this also covalent bond, here also covalent bond, and here extra holes are present and extra electrons are present. Here also covalent bond, here also covalent bond. That is why these covalent bonds are not drawn. It is understood that there are so many covalent bond, but here extra electrons are there, extra holes are there, and this is the representation of p-n junction. Sorry, don't say it is PN junction, because what exactly is going on junction I have not shown you yet. What will take place at the junction I have not shown you, but this is P region and this is N region. As soon as this will happen, what will happen at the junction, we have not covered this. Okay, now I am going to rub this and then I will show you what exactly is going on at the junction and what happens to the junction, why there is some charge is coming, why is there is something is coming, by taking the help of this diagram only. Okay, so please remember that I'm going to draw, delete this, and then I will draw another picture. Now we are going to start from where we have stopped. This is basically the smaller version of the previous slide. So we can say that here there are so many boron, here so many phosphorus atom. This region is called N type, this region is called P type, and this representation of this will be simpler representation of this structure is this one. We have removed all these covalent bond, only what is extra there, and what is extra we have represented this. Clear? And this is basically a junction. We are going to study what exactly is going on at the junction, and that is why this is called PN junction physics. So now I am going to zoom this here, sir. Now we are going to zoom. This is basically a junction, sir, and if you look at the junction, there are so many boron atom available here. Boron, and this is boron with one extra hole, and similarly like this one, and near the surface only, near the junction only, at that time, at that side, there are so many phosphorus atoms are there. Now but these phosphorus atoms are having one extra electron, not hole. Okay, so now this is basically a picture which we have seen. Now extra electron, extra electron, extra electron, extra electrons here in this region, extra hole. But as soon as this picture will happen created now, what happens, this boron and this phosphorus atom will discuss something between them. What they will discuss? Phosphorus atom will say to boron that I have one extra electron, and that is why I am unstable. Similarly, boron will already boron will also say to phosphorus atom, yes, I have an extra hole and I am also unstable. Now let's make a deal. Boron will say, please give me your electron so that I will become stable, and phosphorus will say that please give me your hole, then I will also be become stable. And this deal, because of this deal, what happened, this extra electron will be given to the boron, and while making this deal, this phosphorus atom is giving its electron, and giving electron will create a positive sign, or this will become positive ions, and this is taking extra electron, so this will become negative ions. So now if you look clearly at the junction, few of the boron atom will take the extra electron from the phosphorus atom, and in this process what exactly is going on, near the junction here lots of negative ions are created. Which negative ions? Boron negative ions are created, and here lots of positive phosphorus ions are created, and this process will take place at the junction only. And now this picture will be drawn in this diagram like this one. In the N type there are so many positive ions like this one, and inside the P type region there are so many extra negative ions. See, covalent bond is still present, but no free holes or no free electron near the junction. And that is why if you look clearly this junction does not have any extra hole or extra electron. Yes, they have extra ions, P type ions, and boron ions, and that is why this region is free of charges, free of, not only charges, free of carrier charges, or free, or more, we can say that free charges. And that is why this region is called depletion region. Depletion region. Why depletion region? Because they are depleted of free charge carrier, whether it is electron or whether it is hole. Clear? Sorry, some disturbance was there. So now it is clear. And this picture you are often going to see in the book, in YouTube videos, or anywhere. But remember that how these ions are created. Now you know the reason. How the positive ions are created at that type, at that site. You know the reason. And second, most important is that not this is the exact picture. Behind that, there are so many covalent bond also present. Now from now onward, we are going to draw this picture again and again. Why this is called depletion region, we know. Why this is called p-type region, we know. Why this is called n-type region, we know. How these negative and positive ions are created, we also know. If we look clearly the junction physics, at the junction this deal is getting happening, and with this deal these charges are getting created, and because of this, in this side region there is no free electron or free holes, and that is why this region is called depletion region. Clear? At the junction some depletion region will be created because of this. Now you must be thinking, if you are a good engineer, you must be thinking, sir, while happening this, all the boron atom may be getting positive ions, or we can say that all the phosphorus atom may make a deal. But remember that this deal, while this deal is happening, simultaneously this deal is happening. For example, if we first deal is happening, positive and negative are created. Second deal, positive negatives are created. And if these positive negative charges are created, because of this there will be development of one internal electric field. This is called internal electric field, and the direction of internal electric field is from positive to negative. So as soon as this deal is going on, the electric field is getting more and more stronger. Now what happens when this, then when the boron atom which is far away from this junction will try to move in this region, what will happen? As soon as this hole will get into this electric field, this electric field is much stronger. Now this electric field will exert force on this hole in the direction of this one. So now once this field is created more enough, after generation of this electric field, no more boron and no more electron deal is happening. Now similarly, so many electrons are also want to come into this picture. Again the electric field will exert a force in the, on the electron in the reverse direction. So the electron will be repelled at that time, and the holes will be moved into this direction, and further no more electron and hole are getting involved in any deal. And this is called the thermal equilibrium condition. That means if you don't apply any external bias, ideally this will be the scenario. These holes is not possible to go that side, and these electron does not have any possibility to make a deal with this one, because of the internal electric field which is created by some of the deals between the phosphorus and the boron atom. And this scenario will be there after long time. So this is not going to change, and that is why from now onward I am only going to draw this picture, and we know exactly the every reason. So now from today onward, if you draw PN junction, just draw this picture. So now I'm going to draw the PN junction. So sir, this is a p type region, and this is basically a n type, and in between them there will be a depletion region. Why depletion region? Inside the p region there will be lots of free holes will be available, and in this inside region there are so many free electrons are available. Now inside this region there will be a creation of negative ions, and their side there will be creation of positive ions. And now because of this there will be generation of one in small electric field, and now this electric field will not making possible to go this one, and now exerting an opposite force on the electron, and this will not be going to this one. So no deal is going on, and this is the exact scenario, and this is called the depletion region. I am calling it depletion layer, or we can say dl depletion region, or dr depletion region. Okay, so this is basically a depletion region. Remember that this picture and this picture is basically a picture at 0 Kelvin. 0 Kelvin, and this is very important. Whatever we have studied till now, they are basically at 0 Kelvin. 0 Kelvin, but most of the time we want a discussion at 25 degrees centigrade, or we can say that 300 Kelvin, or we can say that room temperature. Now sir, can you tell me, if this is the representation at 0 Kelvin, what will be the representation at 25 degree or room temperature? Is there any difference in the representation of p-n junction? Yes. Now coming to the discussion in this picture, sir, at room temperature, there is a possibility that in this region and in this region few of the covalent bond will get broken, or the weak covalent bond will get broken by absorbing this temperature 25 degrees centigrade. That means out of so many covalent bond, millions of covalent bond, few covalent bond or weak covalent bond get broken because of this thermal energy. And now if few covalent bond will get broken, what will happen? One covalent bond will involve in two electrons. So now this electron will get out, and this will be electron, and this electron will be this one. And now when electron leaves some space, this will called hole, and similarly here also one hole is present. So if you look clearly, at room temperature, with the breaking of covalent bond, there is a generation of two electron and two holes simultaneously. Similarly, this type of situation may occur in n-type also, and there also one covalent bond will break, one covalent bond will generate two electron and two hole. So in this scenario, sir, only this will happen. Few of the covalent bond will break out. Suppose one or two, suppose one covalent bond is getting broken because of the room temperature. So this will create two electrons and two holes, and here also this will create two electron and two holes. Now this is the exact representation of p-n junction at 25 degrees centigrade. At 0 Kelvin, these few electrons are not present, these few holes are not present. So now from today onwards we will remember that this is 25 degrees centigrade temperature representation, and inside the p region there are lots of holes, and these holes are called majority carrier concentration. Majority carrier concentration. And these electron which is generated due to breaking of covalent bond, it is called minority carrier concentration. Similarly, in n-type, these are electrons, and these are called majority carrier concentration in n-type, and these holes are nothing but the minority carrier concentration. And now this is your depletion region, this is your internal electric field, and this is p-type, this is n-type. If this is not present, this is the picture of 0 Kelvin. Now but this is the picture of your 25 degree centigrade. Let me recap once again. From now onwards, I am going to draw the PN junction like this. So from now onwards, we know how to draw the PN junction and what is the exact meaning of that. So now this is basically whenever anyone asks you to draw the PN junction, so sir, this is the PN junction, so this is P type, this is N type, and now we know in between P type and N type there will be one region, and that region is nothing but the depletion region. Why it is called depletion region? Because it is depleted of the charge carrier. Which charge carrier? Free charge carrier. Now what is the region containing? This will contain negative ions and this will contain positive ion, and because of this ions there will be a development of one internal electric field EI. This EI will not allow these holes to come to this side to make a deal with the electron, and neither the electron from this side will be allowed to make a deal, and this will be the situation. This will be the holes, and so many holes are there, so many electrons are there, so many electrons are there. This is the picture at 0 Kelvin, but most of the time physics of semiconductor is understood at 25 degrees centigrade. Now I am going to draw, this is basically an electron, and this is electron, and this is hole. So these few electrons are generated due to covalent bond breaking, and these few holes are generated due to covalent breaking, a covalent bond breaking because of the thermal energy at 25 degrees centigrade. And this is the picture I am going to draw from today onward. But while drawing this picture, I will remember in my mind that there are so many covalent bonds are present in this region also, inside the depletion region also, here in the n-type region also. So many covalent bonds are present in all over the region. That is why not drawn on this picture. But yes, we will remember in our mind that there are so many covalent bond here, here and here. The only thing is that what is extra in this region? Electron. What is extra in this region? Holes. What is extra in this region is negative ions. What is extra in this region are positive ions. But all over the region there are so many covalent bonds are still present. When now the only thing is left, what is the working of this PN junction? Under two cases. One is forward bias and the another one is second reverse bias. Okay, so this will be discussed in the second video, and hopefully this concept is clear in your mind now. Okay.